Good morning, everybody. I hope you guys are all doing well and fine. Your health is in good condition. So let's continue where we left off. Good morning, Matteo, and good morning, everybody again. Thanks. So we studied last time Fourier series, right? Representation of signals. Remember, that's not for any signal, but for periodic signals. So for periodic signals, because we can find a fundamental frequency, remember, then we know that we can express that signal or decompose that signal as sum of exponential or complex exponentials, which are sinusoids actually, right? Sinusoids that are multiples of that fundamental frequency. Of course, whichever of those harmonics exist in the signal, depends on the specific signal. So let's maybe just we will do just two more examples and move to systems today. So let me share my screen. Okay. By the way, let me check my connection. Just to recap, we said we can express any periodic, right, discrete time signal can be written as, this is last time, sum, let's say k0 to n minus 1, capital N is actually the number of harmonically related sinusoidals that we are using to express this signal. And these guys are, remember, 2 pi over n k. And this was really like our omega 0 hat n. Omega 0 hat, I mean, right? So this is really, remember, the basis function and the basis function set, of course, right? Indexed by k, basis functions, and these are the coefficients, again, indexed by k, right? Indexed by k. And here, this periodic signal, actually sequence or signal x of n is periodic with period. This is important. You have to define the period, fundamental period, let's say, fundamental period, n, capital N. That was the actually here important thing to be able to determine. You have to determine this, okay? Okay, so now we also remember this was our Fourier synthesis equation, and we know how to find AK also, which is Fourier analysis equation through, remember, there is as an extra 1 over n, like normalization, averaging in a way. Now you see, please pay attention, here the sum was over k. Here the sum is over n, okay? Because here I'm summing over frequencies, or frequency index is k. Here I'm summing over the time index. Sum over time index, okay? X of n, remember, is projected onto this time the conjugate of the basis function. J2 pi over n k n. Okay, so this was it. And remember also, AK are periodic with AK periodic also with this fundamental period. So we have this one. Okay, so the discrete Fourier series, the difference from the continuous time, discrete time Fourier series versus continuous time Fourier series. Remember here we had infinitely many distinct or possible. They can be similar, but at least, I mean, they can happen to be the same value, but still it can have, doesn't have to be, can have many distinct AKs. Remember, I mean, the sums were k minus infinity to infinity AK e to the minus j plus j in the synthesis, of course. omega 0 t, which is 2 pi f0 k t. Remember, this was it for the continuous time. Now we have finite number of finite. Actually, it's just n finite, or which is actually n distinct. We can call these harmonic components actually also. This is, I mean, meaning equivalently because they each have their own sinusoid, right? Components, meaning, I mean, these guys mean e to the j 2 pi over n kn, right? Okay, I think last thing I want to do here, by the way, I should note this also, definition. Guys, I think we didn't say it, but it's really just AK squared. This AK squared, the graph, its graph is called power spectrum, its graph, versus F hat, which is K over N, or to this W hat, which is the angular frequency, right? I mean, versus frequency, it could all versus K, or simply K, and it's fine. Okay, is known as the power spectrum of okay, of the periodic signal, of course, in this case, periodic signal x of n. Okay, this is important also to know. So maybe we can do an example, we've done some examples last time. So let's look at this example. Rectangular pulse train sequence. Okay. So let's say in a period it's defined like this. Let's say it has pulse train second. We have to define the fundamental period, say n is 10. This will be a rectangular pulse repeating itself every 10 samples. And in a period, x of n is defined by, okay, 1 for n between -2 and 2, 0 otherwise, okay? So this would be the time representation. So we could maybe just say, okay, 0, 1. Actually, it just has to be 2. So maybe actually I can just use these 0, 1, 2, -1, -2. Then it says to be 0, but we won't be seeing, of course, then 3, 4, 5. I have to start again at 8. Okay, so maybe it would have been better to really do it a little bit dense. Okay. So let's make it a little bit dense. 0, 1, 2, 0, -1, -2. Okay, then 3, 4, 5, 6, 7, 8, it again starts. Okay, so 8, 2. Because 10, I know at 10 we have it, right? Because it repeats itself. Because I know then x of n plus 10 is equal to x of n, right? This is known. So I'm just applying that rule. So then I should go plus minus 2 around it. These are all ones. And the same here, guys. -8, -9, -10, -11, -12. Okay, so and it repeats itself. This is a rectangular pulse train sequence. So it's really the equivalent, remember, is it would be a pulse sequence like this continuous version, right? This is the T version, continuous time, not continuous time version would be this guy, of course. So Fourier series coefficients, you guys can do this actually, but let me start for your notes. You would have to do 1 over, let's say 10, K or N. Actually, I did this even for more general N. Okay, let's do it for N. I can do it for a generic N and minus L to L. Here it's minus 2 to 2, of course, and this is equal to 10. Okay, e to the, and it's 1 in this range, right? So it's 1 times x of n times e to the minus j 2 pi over n kn. Okay, so what is, let's see here, how can I find A0? A0 would be really just inserting n k equals 0 here, sorry, k equals 0 case. Then that would be really sum of 2L plus 1 of these sums of 1 over n, right? In this case, e.g. here, L is 2, 5 over 10, right? Which is 1 over 2. Okay. So guys, when you do this math, maybe let's actually do sum this. Then AK is 1 over 10, n is from minus 2 to 2, 1 e to the minus j2 pi over 10 kn. We can just write these. A0 we've already seen. So for instance, I can go to A1. Let's do it separately because we have just a set of them, right? For instance, A1 is 1 over 10. I mean, I'm going to give this exercise, but just let's do one of them. Maybe k equals 1. I need e to the minus j 2 pi over 10. And you have to really now manipulate this sum. So A1 is 1 over 10, right? Let me sum this up. And minus 2e to the, this is 4 pi, right? So plus 4 pi over 10. Plus e to the n minus 1 e to the j 2 pi 10 plus, right? And of course, guys, n's are there. Oh, I'm summing them up. Okay, summing them up. E to the, then I need an n0. What is it? 1 over 10. I know 1. Then plus e to the minus j2 pi minus j4 pi. So you guys can see we could sum some of these up to get sines, right? Cosine here in this case. So I would really have 1 over 10. I would then need 2 cosine 4 pi over 10 plus, okay, 2's cancel then, okay, but plus 1, okay, plus cosine 2 cosine 2 pi over 10. For instance, I have a general formula, but please check this then. I derive here a general formula. You guys can check. The general is AK is 2L plus 1 over N for K multiples of the fundamental frequency. Okay, you can check this. Then I have 1 over N sine, you guys can check this, 2 pi over N. I will give you the link to the textbook. This was from a textbook. L plus 1 over 2. You can rearrange this in this way. A little bit manipulation. Okay, this is otherwise. It can be written in this way. And you can plot the spectrum. Okay, this is called, guys, by the way, a sinc function. We will see this later. This is called sinc function. It's a sine over sine. Okay. Now plot the spectrum. Okay, for our case, n equals 10, L equals 2. It's gonna be something like k equals 0. Again, 1 minus 1. It's gonna be, actually this sinc has a form like this. Maybe I can do an envelope. Envelope is a sinc function. Okay, typically it's something like this, but it has to repeat, of course, so it's gonna be 10 minus 10 repeating itself. I think at 2 it goes through 0, at 3 comes here, 4 again goes through 0, and 5 is here. Okay, so it should be 6, 7, so I should have that. And then we go back to repetition. This is K. Okay, it should just start repeating itself. So do the same here. Minus 3, 4. 8, and then repeat. Starts to repeat again, right? 9. Okay, these are minus, of course, by the way. Okay, so I think we got the point. It should just repeat itself. It's periodic, right? So it should just, so maybe like here, you can see the periodic form. Okay. So important thing is, while you add these, exercise, please derive this. Derive this expression. Also here, I can say maybe you should show these, because this was a real signal. You guys should, when I found A1, I know this is equal to A1 plus, this is here, n was 10, right? So this should be also A9, for instance, right? Also equals to A1 minus 10, sorry, A minus 9 and A11, of course, with its periodic, okay? This is periodic. What else? Then I know this guy is also equal to A minus 1 conjugate, okay? If it's a real result, of course, they will be equal. So, I mean, recall that AK here for real signals, AK conjugate, and always we have, of course, AK plus n is AK. That's already there. Okay, so maybe just to show you something, guys. I'm trying to see. Let me, here, when you start partial sums or adding these, let's see. When you start adding these, actually, AKs for the periodic square wave, okay, you will see that as you add more AKs, you will have a better approximation. This could have been another square pulse with different parameters, but important point is, yeah, it's, you see difference, I guess. We have -1. No, it's the same, 9. Okay, it repeats itself every 9 samples, not 10 here in this case. Look, 9, 18, -9. Similar, it's non-zero between -2 and 2, but capital N, or the fundamental period here, was 9. But you see, as we add more AKs here, more sinusoids, harmonically related sinusoids, we will have, or we will come close to an approximation of the sequence, which is actually at the end almost exact, right? Here it's exact. Okay, nice. Now, I think that should be fine. I want to see if every year I show these nice videos about Fourier series. Maybe I can show just for a few minutes to wake you up. Now I found I opened it up. Guys, about the harmonics and how, for instance, Beethoven used it. So let's check it out actually. Now I'm thinking it's a good place before we leave Fourier series representation for now.
It may sound like a paradox or some cruel joke, but whatever it is, it's true. Beethoven, the composer of some of the most celebrated music in history, spent most of his career going deaf. So how was he still able to create such intricate and moving compositions? The answer lies in the patterns hidden beneath the beautiful sounds. Let's take a look at the famous Moonlight Sonata, which opens with a slow, steady stream of notes grouped into triplets. 1 and 2 and 3 and But though they sound deceptively simple, each triplet contains an elegant melodic structure, revealing the fascinating relationship between music and math. Beethoven once said, "I always have a picture in my mind when composing, and follow its lines." Similarly, we can picture a standard piano octave consisting of 13 keys, each separated by a half step. A standard major or minor scale uses 8 of these keys, with 5 whole step intervals and 2 half step ones. And the first half of measure 50, for example, consists of 3 notes in D major, separated by intervals called thirds that skip over the next note in the scale. By stacking the scale's first, third, and fifth notes, D, F sharp, and A, we get a harmonic pattern known as a triad. But these aren't just arbitrary magic numbers. Rather, they represent the mathematical relationship between the pitch frequencies of different notes, which form a geometric series. If we begin with the note A3 at 220 Hz, the series can be expressed with this equation, where n corresponds to successive notes on the keyboard. The D major triplet from the Moonlight Sonata uses n values 5, 9, and 12. And by plugging these into the function, we can graph the sine wave for each note, allowing us to see the patterns that Beethoven could not hear. When all 3 of the sine waves are graphed, they intersect at their starting point of 0, 0, and again at 0, 0.042. Within this span, the D goes through 2 full cycles, F sharp through 2.5, and A goes through 3. This pattern is known as consonance, which sounds naturally pleasant to our ears. But perhaps equally captivating is Beethoven's use of dissonance. Take a look at measures 52 through 54, which feature triplets containing the notes B and C. As their sign graphs show, the waves are largely out of sync, matching up rarely, if at all. And it is by contrasting this dissonance with the consonants of the D major triad in the preceding measures that Beethoven adds the unquantifiable elements of emotion and creativity to the certainty of mathematics, creating what Hector Berlioz described as one of those poems that human language does not know how to qualify. So although we can invest...
So I hope you are also really amazed by this analysis of Moonlight Sonata, Beethoven's one of the most, I think, beautiful pieces. And you guys now can follow, I believe, you were able to follow here these things where, you know, it's talking about the harmonics. Here it was like, I think 2.5, 2 times 2.5 and 5 multiples, not exactly the integer multiples. I think it was 2, 2.5 and 5, right? But still, you see the harmonic frequencies other than the 2.5 times. This is a special case of course. I mean, consonance is something, some analysis these people created to be able to explain what Beethoven was using. And then there was the dissonance, right? I mean, I think it's really beautiful. And you can follow these now, like where each of these, for instance, curves here, the red, the pink curve, the blue, green, they are each a sinusoidal curve, but actually they are each a note, for instance, on the piano, when you press an A or D, right? So I hope you enjoyed it. If you want to listen to it again, we can share the link. Guys, now that should be all for the Fourier series representation. Let's start with the systems now. By the way, I mean, any questions before we move on to the new topic? Are we guys fine with, or at least clear to a degree with the Fourier series representation, both in continuous time and discrete time? Well, I think one final example before we move on. I just realized we could also give as an example, periodic impulse train. Yeah, let's do this also. Okay, guys, I was gonna do this and I forgot. Now it's here, periodic impulse train. This is, remember the impulse function or sequence in discrete time, easy to define and use. It's really, okay, it's defined in this way. It has a fundamental period, capital N, okay? And I will be shifting these guys infinitely many times, okay? L minus infinity to infinity. And for instance, it's 1 here, this delta n sequence. I'm plotting it now. And every n, so let's maybe make it here. Every n, it's gonna repeat, or it will have this value 1, the same one. So this is really delta of n. This is delta of n minus n, right? Delta of n minus 2n goes in this way. And on the negative side, the same thing. This is really delta of n plus n. Okay, etc. So this is called an impulse train, meaning an impulse function repeating itself every n samples. Okay. So this is how it is defined. I'm asking you, what are the discrete time Fourier series coefficients of this signal? Fourier series coefficients of x of n, what are they? Okay, so this is really relevant. So this is, I need, okay, let's maybe do it. I was gonna give it as an example, but do you guys have a question? Yes, I think you guys probably replied, we are almost clear part with the Fourier series representation. Okay, so let's apply our definition, right? What is the definition of Fourier series coefficients? 1 over n, n0 to n minus 1, sum. I can sum over these harmonically related basis functions multiplied by the signal itself. So this is really actually an inner product of the signal with the basis functions, harmonically related sinusoid basis functions. Okay, here x of n is delta n, and you see I'm taking it in one period. That's important. And in that period, one period over one period, sum over one period, and in that period delta n is equal to 1. Really, so I really have n0 to n minus 1. Okay, delta n is 1, which is e to the minus j 2 pi k n n. Remember, we know this was actually, this guy was equal to 1. We've looked at these basis functions. Whenever actually it's on the 0 and multiples of n, it's 1. Otherwise, it sums to 0. There is a zero sum property. That's why the contributions from everywhere else is 0, but only the contribution comes from n equals 0 in this case. So that's why we have 1 over n. Okay, so in the end, these are AKs. The spectrum, let's look at the spectrum. This was X of n. Now let's look at spectrum of X of n. Okay, graph. Let's just plot this guy. K, it's a function of frequency, of course. So this is my AK axis. You see, AKs are, again, these discrete in a way delta n, but with amplitude 1 over n. Okay, so let's maybe do again these 1, 2, 3, the indices, K indices. These are actually, remember, corresponding to multiples of a fundamental frequency, but here it's all in the discrete representation, -5, -6, -7. Okay, so this was 0. Now let's just plot everybody, I mean, all of these guys. Okay. It's repeating itself also, right? Because it's periodic. Okay, so it's really AK for all K is 1 over n. I mean, it's really an infinite sequence of delta. We can just express then this delta and n as, we can say, also use Fourier synthesis. Okay, then I have X of n, bring in the AK, okay? K 0 to n minus 1. Now AK were 1 over n e to the j 2 pi k over n, right, for all. And this was, okay, this could be deduced from what we've just done, inserting AK here. This was AK, remember. This is one representation for the, actually another representation for the periodic impulse train, delta n. So actually here, guys, this was X of n, right? So this is the definition of the impulse train in using the shifted impulses in a way, right? It's a sum of shifted impulses. I can also represent it in terms of the basis functions, as you see here. So I think that's nice. That's fine. And the spectrum can be represented also as an infinite sum of, in a way, delta functions, but let's not go to that because it's really, we know this is a periodic spectrum. So I think that should be it. That was the last example we wanted to cover. Okay, so now we could go to start with systems. I think that's chapter 5 in the textbooks. Please check, but it should be chapter 5. Now, systems. We've defined this before, but what is a system? Because we talk about signals and systems. System is actually something that maps an input signal to an output signal. Okay? Maps an input signal. It could be any data, of course. Input data, for instance, I could say. Maps an input to an output. It could be, again, a signal, of course, or, I mean, you can define it as a data signal or whatever, a specific output. And actually, this is really like algorithms, right? Probably you've already taken our algorithms one. Algorithms are also takes an input, takes, of course, a set of parameter system also, or a model, right? A system model. And they do the same thing, right? Map, and then they map an input to an output. It's the same thing for us. So let's say they are equivalent. So we have continuous time systems and discrete time systems. Continuous time, let's say, takes the only difference is takes a continuous time signal and maps it to a continuous time output. For instance, circuits, real physical, for instance, RNC circuits, resistor capacitor circuits, they are continuous time systems. Discrete time systems, however, take this discrete time signal and map it to a line, let's say, of course, map it to a discrete time output, right? YFN. So, for instance, an example system, guys, example system. Let's say you are in a room or in a concert, in some place, in a meeting, you are recording, of course, this is wherever you are allowed, continuous time. Sound waves come into the microphone, let's say, okay, microphone, let's say. There is a transition from, in the microphone, there is these transducers which convert one form of energy into another form of energy. Here it's acoustic waves that are coming, okay, acoustic signal. That is converted into a digital signal, right? First of all, electrical signal before digital. First of all, converted to acoustic to electrical. I mean, this is, of course, in the realm of electrical electronics engineers, but we should just know what is happening here in the system. Then there is an analog to digital converter. We sometimes call this continuous to discrete converter. Now it's a discrete time system, right? A digital system, X of n. Now, let's say I saved it as with an compressor. So compression, remember, is another system. Remember, systems, or we manipulate signals, or a system may have multiple purposes. For here, for instance, the specific continuous to discrete. Its purpose is really convert these physical signals, continuous time signals, into the digital signals. Okay. Now, for instance, MP3 compressor. Let's say it's in this way. MP3 compressor. This is a compression system. Okay. Now let's say I have an X prime or another discrete time signal. It's compressed. Now, for instance, I may, most common form of systems are filters, right? I may have, for instance, a filter system, a filtering system. And I obtain another discrete time signal. Maybe filtering is the most common, and maybe its goal is to here remove some noise, or maybe uncompress, actually, filtering. Maybe I could say, okay, let's say this is filtering in the filtering system. Most common form, we try to filter signals to extract information, features, and things like that. Yeah, there can be an uncompression signal system. Let's say it's in this digital to analog converter. I mean, there can be an uncompression system here too. But maybe, okay, it just goes directly to digital to analog converter, or this is discrete to continuous converter. And here at the end, I have y of t. My output could be actually just somewhere here. It could be just a discrete time signal here, which is compressed and saved in your hard disk. Okay, so guys, this discrete to continuous to discrete, discrete to continuous, we will study again. We've seen already continuous to discrete, but we didn't see this. We will cover these notes. We will cover these after we cover Fourier transform. Okay, we cover Fourier transform. Okay, so I mean, this is an example system which actually starts from a continuous time signal. Let's say actually here what could happen is you may directly go from the compressed signal to an uncompression, then to a discrete to analog converter. This would be like your speakers, right? And you play the music here, for instance. So continuous time, but with discrete time processing in the middle, or you can already start with a discrete time signal, some data, for instance, discrete data, and start working on it. So we said systems for removing unwanted features such as noise, etc., such as noise, etc., from signals, right? From signals. Because a system manipulates a signal, remember. They are manipulators of signal. So, for instance, filtering, we said filtering. Because in filtering, we believe signal is corrupted with some information, some noise. And we then say X of n goes through this filter, input is mapped to output, and here you know that you have a prior information about the corruption. Okay, you have, of course, you may not, but you have to design this filter. Okay, design the filter with your belief or assumption about the corruption. For instance, we will see some example filters. The most common filter is a smoothing filter, averaging filter. Okay, corruption or unnecessary parts, let's say, unnecessary components in the signal. It could be actual low frequencies. We will see what that means later, but you may be after more abrupt changes, or you may be after smooth parts of the signal. Okay, so belief is that our belief, let's say we believe input is corrupted with noise, or input needs to be simplified. We sometimes simplify, meaning we get rid of unwanted parts in the signal. This is another thing. There are also systems that try to invert some effects, physical effect. For instance, this is a typical example in telecommunication systems. Let's say you have your cell phone, okay, cell phone. You talk, your voice signal converted, of course, through the antenna of your cell phone, goes to some transmitter station, okay? And also, while actually going through the communication channel, actually being transmitted, it may get reflected from some buildings, but it may also be directly going to, let's say it's going to a base station here, okay, some base station for cell phones. I mean, we're not communication people, but just the general idea, of course, we can understand. My point here is this X of t is generated, e.g., say your voice. Okay, it's generated and sent to the transmission channel. Then it's that X of t may get reflected from some buildings and other objects in the surroundings. So at the base station, your signal could be something like this, the obtained signal, received signal. Okay, y of t, this is received signal. It's the signal x of t plus some alpha, some parameter times x of t minus tau. By the way, filters or systems, they have some parameters. I should probably say they have parameters and they have a hypothesis function or a model, okay? A model plus parameters, they have to be defined. Depends, of course, parameters depend on the parameters. A model meaning, first, if it's a smoothing or averaging filter, that's a model. If it's a high pass filter, that's a model. Parameter is, for instance, if it's an averaging filter, how many signal coefficients I am averaging in one shot, okay? So here, for instance, this is something that is a part of the model, a parameter of the model. We will see it helps into the decay, modeling the decay. So here, let's see. Okay, I think, yeah, what I'm trying to do here is I want to show, this is a, by the way, just for illustration. Our goal will be here in this, in such a case, engineers actually, this was transmitter system, the transmitter, right? You see, actually, it inserts some unwanted components in a way here, that's echo part. This is the echo part of the signal. Echo, and goal is to undo that, to get rid of that. So here the goal is, for these communication engineers, to come up with a system which is the inverse, actually, come up with the, let's say, inverse system of H, to undo the effects of H. Okay, that's the idea. Then you get an x tilde of t, which is hopefully almost x of t. That's the goal. Okay, you can read this example, guys, in the textbook. I think this was in the probably let me see, chapter 4 beginning or chapter 5 beginning. But here what it does is, let me tell you, x tilde of t, this system, inverse system, takes the, for instance, it was defined in this way, takes the y of t and multiplies its shifted versions, okay, with alpha and subtracts and adds them a multiple of times. One times shift, subtracts, multiplies by alpha and subtracts. This is a side note. And then 2 times shift, multiply by alpha square. 3 times shift, multiply by minus alpha cube. Okay. When you do this, guys, insert the original model, insert this guy here, here, and here, insert. You will see that in the end you end up with really something like x of t. This will be really almost x of t, because plus it will have some components in terms of alpha to the 4 x of t minus, I'm just making this up, but some shift amount. Okay, let's say 3i. This is if alpha is much smaller than 1, hopefully, in your parameter set, and in the, of course, in the system. This is introducing it actually. This part can be ignored, and you see, you recover the original signal. That was the goal, right? That's what you transmitted. Say your voice, you are talking, or it's a music you are sending to your friend. Then the goal is to recover the same thing with an imperceptible error on the other hand. Okay, that's the, this is inverse system. Okay, okay, it was t minus 4 to the, let me write it exactly then. Just a sec, eraser. It was, I'm gonna write the full equation here. t minus 4 tau. That's the echo part being killed, because if alpha is less than 1, this alpha to the 4 is really small. Okay, so you kill the echo. Here I should say echo is killed. Echo part, which we don't want, okay? This is an example of an inverse system. Let's write it in inverse. This is an example of an inverse system. So, and try to eliminate unwanted parts in an image, in a signal, sorry. Parts or echoes in this case. Parts, okay, let's say here it's echoes in this case, okay? In the signal. Okay. So is this clear somehow? Here, this was the receiver part. I mean, in the receiver, we did this actually. Receiver takes yt, and then inverse system kills the echo to get almost x of t. Okay? And another system, you guys probably know this better than me, an RC circuit. It could work as a low pass or high pass filter, or for other purposes. For instance, this is a capacitor, this is a resistor, RC circuits, this is a system, right? Analog system. And for instance, input is the voltage here. Remember, output is the voltage at the capacitor, okay? Then here we have, we can say this system is modeled by a differential equation, for instance, dy by dt plus 1 over RC. You are not responsible from the circuits, okay, or the ecosystem, but it's just something, some intuition you should know. You can solve right from here, and here RC are the parameters of the system. From here you can solve the output voltage, and you can manipulate the input voltage, right? In some certain ways given by this differential equation to get an output voltage. This is differential equation, right? System is represented as a, let's write it in that way. Here, continuous time system can be represented by a differential equation, okay? You guys know the differential equations, so this should make sense. Today we will start in this next hour discrete time systems, where we will have difference equations, the discrete time equivalent of differential equations. One final thing before we go to the break. For instance, because I know you guys know this well, or at least everybody in our field now knows these, heard about these neural networks, for instance. They are also systems you can think of. They map an input to an output. This is a nonlinear system example, okay? Nonlinear system example or algorithm. You can think of a sequence. These are discrete, right, for us, because they are in our computers stored as matrices, vectors, arrays, and whatever the form is of your data is tensors typically. So neural network system, okay, this is, it has a parameters, okay, let's say the most basic one B, but actually we have millions of parameters in the deep neural networks. Deep enhance, millions of parameters. We're trying to solve. Output is another signal, discrete time, but the most basic is a combination of linear and nonlinear components. So for instance, I can say G of, let's say this theta maps, theta is a matrix that maps the input to an output. So I can start here, theta x is a vector, let's say, a nonlinearity, okay, another mapping, a nonlinearity, Okay, and another one, and this continues in this way. This is the model, what we call a hypothesis model. So system is about designing, coming up with these different models to manipulate an input signal and to give us the desired effect manipulation on the input signal to get an output signal. Input, output, okay? That's it. That's what a system is. Any questions, guys? Systems are easier a little bit probably for you to understand, but we'll cover these finite impulse response systems. We'll cover linear time invariant systems. In the next hour, we will cover then convolutions, but let's see how the time goes by. See you in the next hour then. We just did an introduction to systems and we wrapped up the Fourier series in this first hour. Okay, guys. Okay. Okay, all right. So we were talking about some systems, and actually I was saying, I think differential equation and difference equation systems, we will be looking at these soon. So maybe, okay, so let's go to those a little bit later. Just say, recap, guys. Systems model effects of a physical, model the effects of a physical phenomenon. For instance, mechanical engineers do this a lot. For instance, suspension system of a car, you can write a differential equation. Of course, for electromagnetic waves, their travel and things like that, acoustic waves, sound systems, you can write a model and write a system to model the effects, or we can implement desired effect on the signal. Okay, that we recorded, for instance. This is on the data. So machine learning systems are actually, machine learning is an example, e.g. machine learning systems. Okay, they implement a desired effect, for instance, on the data. For instance, they extract features from the data, right? That's a feature extraction system from the data. Okay, so now we start with, guys, discrete time systems. Systems DT, we know this, we use the acronym DT. So discrete time input signal, X of n, goes to a discrete time system. Let's say it's shown by an operator T, operator. So there's an operation, right? There is an algorithm that models the system. Y of n, okay? So we know, and we can say, I know my T, operator T, maps the input X of n, okay, to the output. So T maps the input to X to the output Y. Okay? So it's like a mapping. T is an operator, or let's say a mapping. So maybe let's get started with some example systems. Okay? Some example. We typically also say we want to write, actually this is really like an input-output relationship. Input-output, we show this or write this by typically IO, input-output relation of a, so T actually models input-output relation, right? Maps the input to the output. So now, example, we sometimes show a system as a block diagram with S, X of n, system S, okay, Y of n. So it's IO relation, input-output relation, let's say, of the system S is given by, okay, is given by, let's say, Y of n. This is the most direct form of expressing input-output relationship, or how the input is mapped to the output, okay? So let's say it takes the input value, it's and two shifted values, 1/3 x of n minus 1 plus 1/3 x of n minus 2. This is what is called a 3-point average system, guys. This is called a 3-point averaging, or average, let's say, averaging system, average system. We will generalize this, of course, to an n-point average system. So this gives us a map or a rule. It's a map or a rule that says, let's say a rule actually, that says output at time n, okay, output at time n, let's say, this is important, n, okay, let's just maybe not make it special, time n is average of 3 consecutive inputs. So let's give an example, e.g., let's give an impulse signal. Say x of n is given by okay, so this is my x of n, 0, 1, 2. Okay, my input, okay, let's also draw the output here, output axis. Okay, and let's see how y of n is calculated. So the input is given by this simple 1, 1, 1, and it's 0 everywhere else. Okay, so let's say my signal is just 3 non-zero values, 3 data points at time points n equals 0, 1, and 2. Okay, and now with this averaging system, just look and see how you can calculate actually the output. It's really taking average of 3 consecutive values. It's like I have a window. So actually here, until here, it was 0, right? So let's maybe first write the axis here, 0, minus 1, minus 2. Okay, let's write 6 also, and goes on like that. So it's gonna be actually 0, right, for all these until here. But at 0, you see I'm averaging these 3 values. So it's gonna be 1/3 at 0. Then it's gonna be 2/3 at 1. Then it's gonna be, when it's averaging everybody together, it's really 1, right? Now it's again 2/3, right? For the 3, because I looked at, am I doing correct? Yes, for 1, and for 2 actually here, for 3, 2/3, for 4, 1/3, right? And then for 5, I would really do this average 3, so 5 is 0, and then of course everybody else is 0. Okay, so you can check, guys, from here, like what is y minus 1? For instance, what is y of 0? I mean, you could have calculated, of course, it through 1 over 3 x of 0 plus, actually it's x of 1, sorry, minus 1, x of minus 1 plus x of minus 2, right? So that's really was equal to 1 over 3, and then you can calculate y over 1, y at time point 1, 1 over 3 x of 1 plus x of 0 plus. So I'm looking at always the current, you see, value, and equals 1 here, and the two previous values, minus 1. That's why this was equal to 2 over 3. Okay, you can, we will see this actually with now as a filter. Currently, we just showed it as an averaging system, but we will show this as a filter very soon. You can view this really as a filter with coefficients we will see 1 over 3. But let's look at some other systems. For instance, example, y of n takes x of n and squares it. This is the square system. I mean, it's really like a functional mapping, right? This is the IO relation. I mean, IO relation is given of x of n, again, goes through the square system S, and y of n goes out, right? This was x of n squared. So now let's give an example x of n, e.g. x of n is given by minus 1, 2, let's say. This is x of n. Let's say it's given as 1 here. Then, okay, it's a 0.5 here. At 2, then it's zeros. Okay, so this is the signal. Maybe let's make it in this way so you can see it. Okay, now square system really produces, right? I mean, the squared values here. Okay, it's just, let me not draw it to scale because it's gonna be really long anyway. So let's just say this is for, this guy will be 1, right? This is 1, this was 1, this 1, 0, 1, and this will be 0.5, 2, and it's 0 everywhere else. So it was really easier to calculate in this case. So maybe let's again show it in this case here. I can have another system, for instance, another averager. Actually, now I'm going to ask you what is the difference from the previous one. 1 over 3. So I'm giving again the IO relation of the system. Another 3-point averager, actually. Averager 1 over 3. Okay, let's not make it in this way. X of n minus 1 plus x of n plus x of n plus 1. So previously, let's look at this previous example. Take the same example and let's see what the output is now. Okay, and it's 0 everywhere else, remember, 1. Okay, now this one, you see, what is the difference from the previous 3-point averager? I'm asking you, what is y of n now? I mean, this is again, x of n goes to this system defined by this IO relation, and y of n comes out, right? So we want to calculate y of n. Okay, let's maybe do it. Just let me do it again. Okay, so what is the difference? Do you guys see, or can you comment on this? Now, you see, for instance, just look at, e.g., look at, guys, y of 1. How to calculate y of 1. It looks at 1 over 3, x of 0 plus x of 1 plus x of 2, right? So this time it's doing a centered averaging calculation. Previously, in this system, it was looking at this current sample and 2 previous samples. Now it's looking at the current sample and it's 2 neighbors, right and left neighbors. So for instance, at -1, I'm trying to draw y of n now, plot. It's this time you see it's looking at 0 and -2, values at 0 and -2. So I'm gonna have a 1 over 3 here, right? At 0, now I will look at these two guys. So it's gonna be 2 over 3. Now at 1, I'm really looking at my 2 neighbors. So it's gonna be 1, okay? And at 2, it's going to be again 2 over 3. And at 3, now this is going to be 1 over 3, 4. And then it's all zeros, right? Because it's not touching anything at 4. Okay, 5, 6, etc. And the same for -2, it's 0 and so on. So you see, this is giving me another signal actually. A shifted version actually, but it's not the same signal. This was 1. Okay. So this is a centered averager. The one was actually the averager system. Now I want us to see a system property here. System property. The systems have properties. Here, what is a causal system? Let's define the definition of a causal system. Guys, output of the system, this is just for causality, by the way, a system property, okay? This is a system property. Output of the system, okay, depends on only the current and the past values of the input signal. Only is important here, only the current and past values of the input. Okay? So, for instance, look at this example. Here, e.g., y of 1 is the output at time n, right? N equals 1. This is output at time n equals 1. And it depends on xn, x of n, at n equals 0, n equals 1, which is fine, but n equals 2. No, this is not good. This is not a causal system. Therefore, this past example, this central averager, 3-point averager, centered, let's say this is centered. Is not a causal system. This is why am I talking about it? This is important for real-time systems. There is something called an online system or a real-time system. So let's write this. Causality is important for real time, or also called online implementation of a system. So the causes of the output, right? Causality, causal. The cause are the values it depends on. They should already be available. That's what it means for an online or real-time implementation. Okay. That's why I wanted to mention. So central point averager, for instance, centered averager is not a real-time implementable system, but this is a real-time implementable. And this is also, it just depends. The value of the output, note here, the value of the output depends just at the value of the input at the same time point, right? At the same time point. That's why this is, for instance, a causal system. This is a note from the ahead of the notes. It's going ahead, but you guys now know it, so therefore it's causal system I'm writing. It's a little bit ahead of itself, but it's fine. So another example, let's look at this 5-point averager. It's 5 points, so it's looking at, you see the current value and plus 4 previous values, okay? Again, this is the I/O relation. Again, I have actually a system here, this system S, and this is the I/O relation for this S, for this system S. Okay? So this time it's a, let's again give an example here. Example input takes an input and okay. I'm just plotting the input now. 1/2, and I'm trying to see, I guess I don't have anymore. Okay, that's it. So here the output, let's look at the output now with this 5-point averager. This is X of n, by the way. Now let's look at Y of n. Let me see. And okay, I'm gonna show you here what is happening. I know it's a causal system. So this guy, let's see, is dependent on the current value and its previous 4 values, right? You see, this is like a very window, filtering window. So -1/2 multiplies by 1/5. This was a 5-point, what we call a running average filter. So this is gonna become, actually, let's write this. Okay, then the value at -1 of Y of n becomes -1/10, right? -1/10. Now this guy looks at 5 points before itself. It's actually really 3/2 times 1/5, 3/5. This is plus, of course, by the way. This is, I was trying to say, this is really equal to y of minus 1, right? 3 over 5, then you can do the math. Similarly, this is 6 over 10. And then, right, I just edit these guys together for 1, which is, this should be 3, right, by the way? Am I, or 3 over 5, yes, 6 over 10. Let's write 3 over 5 also for this guy, I think. This was 3 over 10. This is 3 over 5, actually. Okay? So then you can just shift it one more time. I had 2, 3, again 3 over 5 here, right? I have another one at 2, 4 over 5 here, sorry. Should be 4 over 5. You guys can check actually. 4 over 5. And then I need, this was 1 over 2, right? I'm trying to read my own writing, guys. What is this I'm trying to read? This is 1 over 2, I think. So I would have from here 4 plus 1.5 is 7 over 2, 7 over 10. I mean, please check all these. 7 over 10. At 4, now I should just look at these guys. Three over 5 again, and 3 over 5, and goes on like this. Please check these. At 5, I still have 1, 2, 3, 4. Yeah, I mean, I'm just going with this. So I need to look at, for instance, here, 2 plus 3 over 5. I mean, I'm just very quickly calculating these. Now with 6, 1, 2, 3, 4, I have 3 over 2, 3 over 10. Okay, 3 over 10. At 7, 1 over 10. And then it's going to be at 8, it's going to be 0. Okay, and it was 0 before here. You see how it's calculated, right? I'm shifting a window of 5s, summing things because it's the same weight, 1 over 5 for all the coefficients. That's why it's easy to do here. This is called a 5-point running average filter. Okay. So, I mean, how did I calculate one of these? You just go here and guys, right? For instance, okay, let's take maybe a little bit before. Y of 4 is 1 over 5. X of 4, I need to bring all previous ones. X of 4 plus X of 3, 3 plus X of 2 plus X of 0. You need to sum these up and divide by 5. That's it actually. Here, signal length. You can see something here. Signal, input signal length is 5. We have here, it's a filter, right? Filter length was 5. In the end, you can see that output has length 9. I mean, there is actually, we know what the output should be. Length is 9. So let's call this maybe N. This is M. So this is really N plus M minus 1. Okay. Or I think we typically called filter length L. So let's call it L. L. Use these numbers to find plus L minus 1. Okay. So now let's define a general filter, running average filter. So in general, any questions, please always ask, by the way, running average filter. filter. We can call this n+1 point. Y of n is k0 to m. This is what we did, right? 1 over n+1. You see here, for instance, it was, well, m is 5. We go from 0, no, m was 4, 0 to 4, but we had 5 points, n+1. And the form of our filter in general is this. So e.g., 3-point running average filter, k0 to 2, 1 over 3 x of n minus k. Okay, this was the form of the filter. 3-point or 5-point average. Running average filter, y of n was really k0 to 4, right? 1 over 5 x of n minus k. This is what we just studied here and before. This was the 5-point running average. So we generalize. So you see, this is like the filter weights. BK, filter weights. Here they were just the averager constants, okay? So we generalize to any filter actually. It doesn't have to be just the averaging filter. It's gonna be weighted average in a way. Y of n is k0 to m bk x of m minus k. This is called, guys, an FIR filter or finite impulse response filter. So FIR filter, we will see why it's called like that, but you can from here see finite number of coefficients, right? This is what we have. We will be working with, and here BK are the filter coefficients. FIR filter coefficients. Any questions here until here? Let's see. Y of 4, I think it can be. Let's check y of 4, guys. I need to take 0 and these 3 together. I have, let's see, 1, 2, 3, 4. Mustafa is asking, can we check the y of 4 results here? Is it 4 over 5, guys? 3, 4, 5. You're right. It's 4 over 5, right? 1, 1, 3. Actually, it is, guys, 3 plus 3 over 2, 9 over 2. Actually, now I'm finding 9 over 5, but can you guys check? It should be less than 7 over 4. Let's see. Let's see. I think you're right. 5 is 3 over 5, correct, right? This was 7 over 10. Yes. You're right. Guys, just calculate. Let's write. Let's try. I have it here. You guys help me. What was x4? It was 0. You guys, am I getting 1 less? I was not sure. Now 1 plus, right? Just 1, 2, 3 plus 3 over 2, right? 3 plus 3 over 2 is 9 over 2 times y 5. Isn't Mustafa, is it what you're saying? Mustafa said it should be 4 over 5, so I was checking it because of that. 9 over 10. Okay? I mean, just do the math here. I find 9 over 10. Mustafa says 4 over 5. Guys, you guys, it's 90 people and it's just 1 or 2 people I feel following the class, so it's really not very very efficient. Okay? Don't get confused. It's just sum these up on your own. Okay, Mustafa? It should be, I mean, just guys, I mean, it's this equation, it goes here, right? I just inserted y of 4, x of 4, n equals 4, right? X of 3, x of 2, x of 1, x of 0, right? That's it. Here, x of 0. I think I went one more, right? Why, x of 0, okay, so it's really exactly, yeah. We had to do it here, right? You're right. I mean, exercise, please go ahead and fill it, yeah. Şunu mu diyorsunuz? Denkli şeyi mi? Input'u mu yanlış yazdık? Arkadaşlar artık bu kadarını şey yaptırtmayın bana ya. Onu yapın. Please go ahead and do this on your own. Okay? Bunu niye kırmızıyla yazdım? Is it there or not? Please check. It's there. Just do the math while it's there. I think most of it is correct because I just did it here on the fly. I didn't note it in my notes. I did it on the fly here. Please do the math here, exercise, okay? I mean, come on. This is really easy, okay? Just exercise, please fill in all y of n, okay? Just, you can even write all of them openly. For instance, what is at y minus 1? What is at y minus 2? You know the input-output relation, okay? Just do the math here. It's just summation and multiplication and division. Okay. So, but this should be here, this 1 over 2 at 3. So I want us to generalize, look at this general form of the filter and compare these guys to the general class of differential equations and difference equations, okay? So let's look at this. General, so we will do this comparison. So this is a recall for you. I think you guys taken ordinary differential equations, linear, constant, coefficient, differential equations. This is differential, okay? So for instance, this is an example. Plus, remember, this is defining a differential equation, d2 y of t by dt squared plus, I mean, this should be an a2, there should be an a2 here. Plus a0 y0 t. And on the right-hand side, I can have actually bk d to the k y of x of t by dt to the k. Okay? K0 to m. Okay? So the general form of these were, this is, again, I'm assuming something you've studied in your differential equation class. Okay? AK, K0 to n, AK, d to the k y of t, I'm writing it again here, dt to the k, sum bk d to the k x of t over dt to the k. Let's say this is k0 to m. Okay? This is the differential equation. Now, actually, what we're looking at is the difference equation, equivalent difference equation. So this was continuous time, right? Now go to discrete time, difference equation. Okay, so I can really say k0 to n. Let's maybe write it a little bit less to leave space here. K0 to n, ak, yk, y of n minus k, k0 to m, bk x of n minus k, okay? This is the general class of difference equations. This is also linear constant coefficient. Difference equations in a way. This is the most general form of it. This is a system, guys. So an x of n goes in. This is a general system. To this system, this is the IO relation, let's say. And the y of n goes out, IO relation, okay, of this system is given by this. However, you may notice something here. The output depends on its own. When the output depends on its own previous version, samples, that will lead to a recursive system. But we won't be. These are called infinite impulse response systems. That's a more advanced signal processing topic, actually, and not much related to us. In this course, at least, we cover A0 equals 1, all other AKs are 0 when K is not 0. This leads us to this only when AK or A0 is 1, Y of n, right? K is 0. Y of n is equal to K0 to M BK x of n minus K. It leads us to this finite impulse response or this system of equations. This system, at least with this IO relation or IO equation. Here you see the output at time n, guys, depends on only the input and its values at actually in this case only previous current and previous values. So this is actually a causal system also. And it does not also depend on past values of the output. If it depends on past values of the output, you have to go to, like I said, some recursive formulation. But for us, we are interested in filter coefficients that are really like windows that are slide over, that can be slided over our input data, and then we can really calculate them efficiently by these finite impulse response systems. Okay. The other, actually, guys, this AK not zero case, the general case, relates more to electrical electronics engineers. That's why I'm skipping that part. In this class, I didn't include it in our course content because it's already a lot of it's very much loaded, already a lot of content and material. So if you are interested in that, you would have to go to, I think we have a class in 4th year. So it should be really, this is an introductory signals and systems. It's in a next level class. Okay. So we will, I mean, for you, it's not really important. It's nothing that you will ever use. This other one, this more general one. For us, most important one is this finite impulse response or FIR filter. Okay. So this is the system that we will be mainly working with in this course. Don't really dwell on it much because the other one is really not something useful for our purposes. So let me just try to add a page here. Okay. So for us, we said y of n b0 x of n, okay, plus b1 x of n minus 1 bm x of. So this is the FIR filter I just wrote, okay. Really, x of n goes, the FIR filter or system helps us to calculate the y of n. So example, bk, for instance, I can give those bk's. You see, I have bk, set of bk filter coefficients 1 to or 0 to m, okay, filter coefficients. So for instance, I can say I can give them as 2, 1. If this is B0, this is B1, B2, B3. What is the I/O relation of this system? For instance, question is I/O relation of this system, okay? And I'm asking you also, is this a causal system or not? These two are the questions. So what is the I/O relation? Answer 1. This is question 1, question 2. Answer 1. Just go and say, see, you can see it has a finite number of filter coefficients. It's really going through n minus k, k0 to 3, right? And this is really equal to bk is for instance 3 x of n plus, okay, minus 1 here now, minus, let's say minus x of n minus 1 plus 2 x of n minus 2 plus x of n minus 3. Okay? So this is the input-output relation of this system. This was, as we see, an FIR filter. Is it causal? I can ask you this. Is this a causal system? Yes, yes. Okay. Yes, causal system. And I can also say, I think we've said it, but just for the notes, filter length here is, you see m plus 1 runs from k0 to m. We call this L. We call this filter order M. So here in this case, L was 4 length filter, M, so it was a third order filter. Okay, and x of n of length n, given x of n of length, let's say n, we call it an endpoint signal. What is the question? What is length of yn? We've done this already. We know it's n plus L minus 1. Okay? You can see this is valid for all FAR filters. Yes, it depends only on the current and past values. You're right. So now let's, guys, do you have any questions? I'll give a break, 10-minute break, and then we will start with other system properties. We've seen causality. We will look at linearity and time invariance. So we'll look at LTI systems, okay? After this one, after the break. We study them, and I think that should be it for today. LTI systems. Then next week we can start the convolution actually. Any questions until here? We've defined actually these finite difference equations, and we've looked at the finite number of filter coefficient part here, or finite length filters actually, finite length filters with BK. Because our goal is to be able to write, like I said, implementable filter, numerically implementable by a convolution operator, and with a finite number of filter coefficients. Okay, so see you after the 10-minute break then. We meet at 10:50, okay? So, okay. So let's get started and wrap up actually with a new topic, by the way. New topic meaning subtopic of these properties of linearity and time invariance. So let's continue. Yeah, by the way, I mean, I just calculated these very quickly in the break. Just corrected these. Please do this on your own, okay? Then because you can see this example, for instance, how to calculate given an input output relationship, filter relationship, how to calculate the output, okay? So now let's see the system properties. System properties. We've already done causality. So causality, I mean, or studied at least this guy. Now, important property is linearity. Means a system being linear means it satisfies property of superposition, guys. Satisfies the property of superposition. This means if I, for instance, have multiple inputs, let's say 2 for now, 2, I actually manipulate those 2 inputs separately by the system, get the 2 outputs, sum them up. That overall output is equal to actually sending the summation of the 2 inputs to the system. Let me write it. It's going to become more clear. So sum of inputs, okay, sum of inputs, if it goes to the system, let's say, sum of outputs. This is the idea actually. Superposition. Sum of inputs goes in, sum of outputs goes out. Okay. And I can scale the input also, superposition, scale the input, meaning, for instance, e.g. double the input, double it. The system S, okay, doubles the output. Or doubled, I get doubled output, let's say, that's better. Or scaled. Scaled output, okay? Let's say this way. Okay, so this is more formally written in this way. So let's write it in this way. A times x1 n plus b times x2 n, let's say, goes in. Okay, this is sum of inputs, right? Goes into the system. I have a y1 n plus b y2 n. But this would be equivalent to getting x1, scaling it by a. Now I know I would get, if x1 gets y1, this would get a y1 n for a linear system. Similarly, take b, scalar b, multiply, take another input x2, goes through the same system, right? I get b y2 n. So you see y1 is the output to the x1 out of this S system. Y2 is the output of the system S when x2 is input. You see this equal, these two summed up. They are equal, right? This is how we will be testing the linearity. So just to sum up, testing, we will do some examples. Testing for linearity, okay, of a system, of course, of a system S, okay. This is important here, the linearity, we are testing for linearity of a system. Any questions, always ask, by the way, please. One. So I will, like we said, you will take 2 inputs, pass them through systems S. Okay, Y1, obtain 2 different or separate outputs. Now pass them through this scaling, okay? Let's say this is multiplied by A, this is multiplied by B. These are added up, superposed. Okay, I get a y prime n, which is equal to really a y1 n plus b y2 n, right? This is what I get. And then actually, is this equal to, I mean, I can implement the system in this way, or this system, I mean, execute the system in this way, two separate outputs separately pass through the system, or sum these inputs up. I mean, you can, of course, write here ax1 plus bx2, but just for this first sake of, I mean, first writing, for the sake of our notes, this is now ax1n, right? The scaled input 1 and another scaled input 2 goes through the system S together. This is, let's call another yn. Is this equal to, the point is, r yn and y prime n equal. Here the question you ask is, is yn equal to yn prime, y prime n? If yes, S is linear, okay? So I think let's see it on an example. That would be much easier. So, or okay, let me first define the second important property and then let's see it on an example. 2, time invariance of a system, because then we'll check them just back to back, okay? System. This is really like saying system behavior should not change with time. System, we will define it mathematically, of course, but that is when I take an input, shift it, send it to the system, the output should be the shifted version of the output of the original signal input, right? So the testing will be testing time invariance, let's say, okay? So first branch x of n goes, let's first make the first branch as x of n goes, y of n goes out. Now there is a delay system. Delay by, it has a parameter n0. Now this is y of n minus n0. Okay, now in the second one, we first delay the input. Get x of n minus n0 goes to the system S. My question to you now is, this is, let's say, a z of n. Are these equal? If they are, yes. I mean, if yes, okay, is z of n equal to, let's say, y of n minus n0? If yes, S is time invariant. No, S is not time invariant. We sometimes say it's a time varying system. So guys, this is meaning you have a system, for instance, an MP3 player or your smartphone. After a year, is it still working the same? This is really like that. We believe mathematically, ideally, it should work exactly as it is. Of course, these are approximate properties, ideal properties. Because after, let your, for instance, MP3 player or your iPhone, whatever, smartphone, sit there for 1,000 years. Of course, it will wear off, it will break, things may change, but still, this is trying to say after several years, after a month or some time passes, like a week passes, it's still the same system, right? It's trying to say that. So that's the time invariance. And superposition is really also very intuitive. Sum of inputs, does it give me the sum of outputs to the system? So, okay. So now we combine these two properties, LTI, we call it linear time invariant systems. Okay. A system that is, okay, both linear and, of course, the definition is both linear and time invariant, okay, is an LTI system. This is the definition of an LTI system. Okay? This is important. Know this one, please. Also. So now, guys, let's do, by the way, maybe I can define the delay system here. I think I didn't, I see it in my notes now. So let's just complete this. Note, we didn't probably do this before, but what is a delay system you may be like? Delay system. X of n goes, this delay system by n0, I mean, as the name implies, takes x, delays it by n0 and prints it out. That's the definition of a delay system, definition. Okay, delay system. My question to you is delay system causal? We will look at whether it's LTI or not also. Here, I wanted to just introduce it and ask it whether it's causal or not. It will be causal in some cases, right? Just maybe try, for instance, if it's a delay by 2, let's say, and 0 is 2. So I have at the output, so my output depends only at the past value. So for instance, x of 2 goes in, I have x of 0, right? So it's really causal when n0 is greater than 0, right? Or greater equal to. Not causal otherwise. Not otherwise, right? Because, for instance, if it delays by -2, then it will look at feature values, right? So, for instance, x of n goes in, delay system. By this time, let's make it +2. I mean, n0 is -2, let's say. It's better to, n0 is -2. So it's really x of n +2. Now, for instance, let's say x of 2 goes in this time. We want x of 4 at the output. So this is a feature value, right? So output depends on a feature value of the input. So it would not be causal in this case. And 0 is less than 0. Okay? So just for your notes, I think it's good to have this. Now let's look at some examples. For instance, let's look at this squarer system. I'm asking you, is this an LTI system? Let's look at our tests here. Okay. First, whether it's time invariant or not, for instance. Let's just check one. Let's say x of n goes through as x of n minus n0. Sorry, I delayed it already. X of n squared, which is equal to y of n, now goes through the delay by n0. This is really equal to x of n minus n0 squared, right? The second pet here was first delayed input. N minus n0 now goes through the system, right? And it's gonna be equal, of course. So here, this is, let's say, y prime n, and this is really equal. Or let's make it something else, maybe wn. They are equal, right? Yes, time invariant. So I'm doing this example just for the sake of our notes quickly, but you can please anytime ask, is it a linear system? Guys, what is your guess? Is it linear? So I'll just execute our flow. First, pass these through the system, y1 and y10 goes out, okay? Then y2 and y3 goes out, y3 and y4 goes out, y5 and y6 goes out, y7 and y8 goes out, y9 and y10 goes out, y11 and y12 goes out, y13 and y14 goes out, y15 and y16 goes out, y17 and y18 goes out, y19 and y20 goes out, y21 and y22 goes out, y23 and y24 goes out, y25 and y26 goes out, y26 and y27 goes out, y28 and y29 goes out, y29 and y30 goes out, y31 and y32 goes out, y33 and y34 goes out, y34 and y35 goes out, y36 and y37 goes out, y37 and y38 goes out, y38 and y39 goes out, y39 and y40 goes out, y40 and y41 goes out, y41 and y42 goes out, y41 and y43 goes out, y41 and y44 goes out, y44 and y45 goes out, y45 and y46 goes out, y46 and y47 goes out, y47 and y48 goes out, y47 and y49 goes out, y47 and y50 goes out, y50 and y51 goes Now sum these up to, sum these up, scale and sum these up. So I have a y1n plus b y2n. But if I were to start with an actually summed up, scaled and summed up system signal at the input. Okay, so these were, by the way, x1 squared, right, guys? Okay, this was it. Now, this is, what is it here, guys? This was y1, of course. So this will be really, let's say, actually, a x1 and x1 squared plus b x2 n squared. I mean, you have to, of course, take in the effect of the system here, right? Maybe let's write this nicely. Sum them up and take them out. So you have ax1 squared plus bx2 squared. They use only current time values. Now I have summed already, superposed the input. What do I have? Ax1 n squared. I mean, let's first do the full thing. It's gonna be, right, this guy. And as we all know, this is really not equal to, I mean, you would have a x1 n squared plus bx2 n squared plus 2ab x1 and x2n, right? So they are really not equal. And then this is not they are not equal, not a linear system. Therefore, it was time invariant. It's not a linear system. Therefore, it's not an LTI system, not a linear time invariant system. Okay? S is not, or this square is not a linear time invariant system. Of course, you would already see it from the squaring operation, but it's the point is whether you can really show it mathematically or not. Okay? This is the mathematical definition of linearity, what I'm showing here. So for instance, now let's do another example. It's this time reversal system. Takes an input, reflects around n equals 0, so makes it minus n. So systems I/O relation is given. Is this, my question is this an LTI system? This is the last example we do for today, okay? So let's see. Okay. Hi, Fırat, welcome. I will hand it over to you in 5 minutes time.
Thank you.
So let's just check, finish this example. Okay, maybe linear or not. Okay, let's pass it through the system. X1, X2. Okay. So let's write the outputs here, right? I have y1 of n is x1 minus n, y2n is x2 minus n. Now sum these up through scale after scaling, sum these guys up. You have a x1 minus n plus b x2 2 minus n, right? I mean a, b. So now this was the first thing. In the second one, let's just start. I'm just actually skipping that multiplication and addition part and just writing the superposed input here, which is fine. Goes through the system S. Now, guys, I have at the end, just apply my rule, input-output relation, ax1 minus n plus b x2 minus n, right? So this is equal. So we can say this is a linear system, right? Linear system. So now look at the time invariance. Okay. Is this a time invariant system? So linearity and time invariance. Let's check x of n. Let's make it first go through the system S. X of minus n first. Now delay it. Delay by n0. X of, maybe I could have said z here. Another, I mean, give it another variable name. X of minus n0, right? Which is equal to x of minus n plus n0. This is what we get. Now, the second way, first delay the system. Did you have a guess for this one, by the way? Is it time invariant or not? I mean, we should really do these classes interactive. Currently, we're not that interactive, but let me ask, what is your guess? This is really doing a time scaling by -1. So every year I know people get really confused by this, but I have my result here is this one. I'm doing a time scaling here. So my result is really x of minus n0. So you see, they are not equal. So this is not a time invariant system. Not a time invariant system. Therefore, the result, system S, this was really like x of n going to the system S and y of n going out. Therefore, S is not an LTI system, okay? I'll do a few more examples next time. But do you have questions until here? We've defined during this class, this hour, LTI systems. This is all from mathematics, guys. You're not learning something new. Linearity, a linear function. It's really superposition of inputs. When you send it to your functional mapping, it should work the same way as if you were individually executing your system on each of those inputs. It's exactly the same idea. And then you can sum it up, right? Superpose those outputs. Or sum the inputs, superpose the inputs first. Scale also, of course. Scale and sum the inputs. Send it to the system. The system produces the same result as before. That's linearity. Time invariance is really the similar idea, meaning whether you execute the signal through the system first, then delay the output, or first delay the input, then execute the system, gives me the same thing. But for instance, for this time reversal system, this time scaling, so maybe I should note here, system does a time axis scaling, right? Okay, so then here for this one, so this time reversal system was not an LTI system. I think this is fine. Like I said, we can wrap this up next time, go to convolution operation, study convolution, and then it's actually valid for LTI systems. LTI operation you can think of, and then we will continue from there. We will also study continuous time systems, okay? We will define an impulse response function, which is important also. Any questions? I'm leaving now. I'm just stopping the lecture at this point. Okay, so see you next time then. Afrat, let me make you the